All right, welcome back, everybody. Today we're going to be talking about graphs and in specific position versus time graphs. I know a lot of students really do not like graphs and feel intimidated by it, but let's try to take it slow and, try to erase our concepts of graphs and how tough it could be. Okay, so we're going to start right away with a example problem here. So the question is, here is an example. Okay, example over here. Here's an example of a toy's car motion that is being recorded for the first 10 seconds. Use the data recorded to plot the points on a scatter plot. So I know a lot of times looking at this, it's just like, oh my gosh, so many numbers, so many things. What's going on? What's happening? What do I do? And it's just a lot. But anyway, let's take it one step at a time. Again, we have the data table, we have the position, and we have the time. Again, we have the position here, and we have the time here. So anyway, let's take it one step at a time. Um, okay, let's look at 0 and 0. Okay, at time 0, which is right here, it is at 0 meters. Great, so we'll just put a point right there. Now, at time 2 seconds, it is at position 1. So let's look at 2 seconds. Great, and it's at 1 meter. So right around there. Okay. At time 2 seconds, I'm just going to draw, it is at 1 meter right there. Okay, at time 4 seconds, it is at 2 meters. Okay, so this is 4. And then we're going around there. Okay. Time 6 seconds, it is at position 3.1. So pretty close to right there. Oops. And so on and so forth. Okay, so it's going to look something like this. Okay, so hopefully you draw something like that. That's all it is, and hopefully this helped you to kind of see how this works. You've probably done this before, but you probably also feel intimidated by graphs, and that's totally fine. We're going to build that confidence. Okay, so now we're going to talk about a line of best fit. So we do this a little bit, but it's more important just to understand the concept because there's not too many problems related to this. But a line of best fit, okay? So what is the line of best fit? That is this, I believe it's a red line right here. So this line that's going through all of these different dots that we just plotted, okay? That is the line of best fit. Drawing a line of best fit. Use a straight edge like a ruler and move it until the edges of line lines up with the points. Around half of the points should be above the edge and half below. The line does not need to pass through any points. Okay, so that's just kind of how you draw a line of best fit. Purpose of line of best fit. It can help predict outcomes using data points you already have, a lot of times in labs and stuff like that. The slope can help identify a derived quantity, in this case, the speed velocity of the object. And we'll go more into that as we do example problems, how this can help you find the speed or the velocity of an object or of what's being recorded. Okay, so once you have drawn the line of best fit, you can use any part of the line to find the slope. Okay, so we can find the slope. And as we should have learned before, the slope is the rise over run, or the change in y over the change in position or change in x. So change in position over change in time is going to give us the velocity. So let's look at this example, and you might have to watch this again to understand it. But example number 1, let's look at the slope between 0 seconds and 6 seconds. So that means from here to here, that's what we're looking at. So we should know from 0 to 6 seconds, it's going to be around here. Okay. And we're going to do the rise over the run. So the rise is, it goes from here all the way to here, which is around that 3 meter mark. Okay. So that's what we're going to do. It's going from 0 meters right here to 3 meters. Okay. So we have the rise from 3 to 0. And now the run. The run is from 0 seconds, right? 0 seconds to 6 seconds. So it's going to be from all the here to here. Okay. So it goes to from 6 seconds from 0 seconds. Okay. So now we're just doing 3 over 6 and we get 0.5 meters per second. Okay. So the slope of a position versus time graph will give us the velocity. Okay, let's look at example 2. I'm going to do a different color. Let's do this. So let's look at the slope between 2 seconds and 10 seconds. Okay, so now what we're looking for is from 2 seconds. Maybe I'll do a different part over here. Okay, let's do 2 seconds to 10 seconds. Okay. And what we should know about that is, okay, this is going to be the slope. I'm going to draw a little bit different. 2 to 10 seconds right there. Great. Okay. Let's look at the rise. So the rise from 2 seconds to 10 seconds is going to be from here to here. Okay. Okay, it's not all the way at the bottom because at this 2 second mark, it's right here. Okay, so it's at pretty much at that 1 meter point. Okay, I'm going to put even 1 meter over here. And at that 10-second point, it's at this like 5 meter point. So I'm going to even put 5 meters there. Okay, so that's the rise. It goes from this 1 to 5, so 5 minus 1. And then let's look at the run. So the run is going to be from this 2-second point all the way to over here. So it's going from 2 seconds to 10 seconds. Okay, so I'm going to put 2 and 10. Okay, and then what we have 5 minus 1, which is 4, and 10 minus 2, which is 8, and it's going to be 0.5 meters per second. So what you should see is the slope is the same. It's going to give us the same answer. It's going to be 0.5. Okay, 0.5 meters per second. And that should be the case because what we can see with this slope, and let me use a different color, do red. What we can see with the slope is that it's a straight line. It's linear, meaning it's not getting steeper at some point. It's not getting more shallow at some point. It's straight, and that means that even if you're getting the slope from here to here, or from here to here, or from the whole thing, then it should be the same no matter what, because the slope is the same straight line. It's not getting more shallow. It's not getting more steep at any given point. Okay, so I hope that makes sense. Again, watch it again if it doesn't, but also if it doesn't, the example problem should also help out with a lot of things. Okay, so an object is recorded to have the motion depicted in the graph. What is the velocity of the object? So remember, velocity is equal to displacement divided by time, or better known as the change in position. So position final minus position initial divided by the time. So what's the final position? Well, it's going to be ending at this 20 meter mark. So I'm going to put 20 meters. And it's starting at this 0 meter mark. So I'm going to put 0. And what about the time? Well, it's ending at this 15-second mark. And it's starting at this 0-second mark. Oops. Not the best handwriting here, but I hope you understand. 20 divided by 15. And we get 1.33 meters per second. Okay. Hope that makes sense. Let's do this next problem and try to do it by yourself if you feel like you understand it now. I'm going to do a different color because I don't really like this red. Okay. Recorded to have the motion depicted in the graph. What is the velocity of the object's motion? Okay, again, velocity is equal to the change in position over time. So let's just do this. We're just going to be going from 30 divided by 5, and this should be equal to 6 meters per second. Okay. This one's getting a little bit more tricky, so take some time. But let's go to this. So what's the velocity of this motion? So I'm going to take a little bit of a different. So we know velocity equals the change in position. So position final minus position initial over time. And let's kind of look at this one by one. The final position. The final position is actually down here. And that point is actually 0. So it's going to be 0. And the initial position at the very beginning, it is at this point right here, which is 25 meters. So minus 25 divided by time. We're going from, it ends again at this 15-second point and starts at this 0-second point. So 0. So we got negative 25 divided by 15. And that should give us negative 1.67 meters per second. And I hope this makes sense because What's happening is at the very beginning of time, or at 0 seconds, it is at 25 meters. However, as time goes on, it's getting lower and lower. So it's going down as time goes on. So it should be going in the negative direction. Okay. It's as if, let's have like a person here. If this is position 0, there's a guy over here starting out at position 25 meters, and then he's walking towards 0. Okay, so he's walking towards the left or down or whatever it is, but that's what you should be visualizing as you're doing this problem. Okay. Okay, find the velocity of each segment. Okay, this is going to be kind of a lot, but it should be good practice. So here we go. Point A, the velocity. I'm not going to even write everything out just because we should be good at it. The final position is 30. The initial position is 0. The time is from 5 to 0. So 5 minus 0. And this should be equal to 6 meters per second. Boom. Okay, part B. The velocity is equal to the final position, which in this case is 30. The initial position of B right here is also 30. And the time is from 10 seconds to 5 seconds. So I'm going to do 10 minus 5. And 30 minus 30 is just 0, so this whole thing is just 0. All right, part C. And just pause this when you feel like you start to get the hang of it. The final position of C is going to be right here. So that's going to be 20. Minus the initial position is going to be right here, which is 30. The final time is this 15 seconds here. And the initial time is this 10 seconds. Again, it's just a rise over run. So we have negative 10 minus 5 divided by 5, which is going to be negative 2 meters per second. And then D is equal to the final position, which is going to be right here. That's 20. The initial position, which started on the same spot, so it's 20 divided by the time. It ends at 20 seconds. And it starts at 15 seconds. Oh, it's 15 seconds. But 20 minus 20 is a 0, so this is 0. And the last one, E. So velocity is equal to the final position. E ends all the way over here, which is at position 0, minus where it started, which is up here, which is 20. And it starts at 25 seconds and ends at 20 seconds. So negative 20 divided by 5, we get negative 4 meters per second. Okay. I hope that makes sense. It could be a little bit confusing, but watch it again if it doesn't. But this should be a good overview of how all of these problems are done. Okay, so understanding slopes. Let's pretend the following graph depicts the motion of a mouse. Let's look at what each segment tells about the mouse's motion. Okay, so let's say the mouse is starting here at position 0, time 0, and going like this. The slope tells us that it's moving in the positive direction. And since the slope isn't that steep, it should show us that it's slowly moving forward, okay? In this specific slope, it goes 5 meters, okay? Travels 5 meters in 4 seconds, okay? Part B over here, we can see that it's a flat line. And this flat line should show us that it's staying at position 5 meters. So it's not moving up or down. It's not moving at all. And if we could look from the other graph, part B and D had also this flat part. And we can also see that it's not moving. It's going 0 meters per second. Okay. So the mouse has stopped moving. And part C, we can see that this is really steep. It's really, really steep right here. And what is that telling us? That it's traveling a large distance. It's going from 5 to 20 meters. So that's a total of 15 meters in a very short amount of time in only 2 seconds, from 10 to 12. So this very steep slope here is telling us that it's moving very quickly. Okay. the mouse is quickly moving forward. And if we look at the other graph, for example, A, we can see that A has the steepest slope, and it is also going the fastest, 6 meters per second. Okay. Part D, again, same thing. It's at position 20 and stays at position 20. The mouse has stopped moving. And E, again, this is steep, probably not as steep as part C. So, and what it's also telling us is it's at position 20, but it goes all the way back to the beginning position 0. Okay. So the mouse is returning to where it started. Okay. Okay. This takes a little while to do, so that's why we're doing a bunch of example problems. So let's look at this. Which slope represents an object that is traveling with the fastest speed? Pause it if you want to, but we should only be looking at one thing when we're trying to see something that's going the fastest with a position versus time graph, and that is the slope. Which one has the steepest slope? In this case, that is C. Okay. Next question here. Which slope represents an object that is traveling with the slowest speed? Again, we should be looking at which has the most shallow slope, and the most shallow slope is actually D, which has actually no slope. So if it has no slope, it's not moving, and it is also going the slowest. Okay. All right, here. Cindy decides to go to a cow racing competition with Jim. Rank the cows from fastest to slowest. There's a lot going on here, but we're trying to find which one's going the fastest and which one's going the slowest. So again, even though there's a lot of weird things happening, we have Moolinda over here, we have Dolly over here, and then we have Elsie and Bessie over here. Again, if we're thinking about the fastest and slowest for a position versus time graph, we should only be caring about the slope. So the fastest. When we're looking for the fastest, we should be thinking about which one has the steepest slope, and that is Elsie. So I'm going to do Elsie here as the fastest. And then I'm going to say, Bessie and Dolly seem similar, but I would say Bessie has a bit of more of a steep slope. Then Dolly. And then sadly, we have at the end, Moolinda. Okay. And again, we know this by which one has the steepest slope to the least steepest slope, or the most shallow slope. Okay. Okay. Let's imagine what graph depicts a cow. Let's imagine a graph depicts a cow race. What does the graph tell us about Moolinda's and Dolly's motion? Okay, let's start with Moolinda here. So something that's a little bit weird with Moolinda is over here. What exactly does that mean? So let's think of it from the time perspective and the position perspective. Let's think about, okay, when does Moolinda start moving? We can see that right from the beginning, we're going to call this time equals 0, Moolinda is moving. Okay, so nothing really moving slow, but moving from time equals 0. Okay, but now let's think about the position. Okay, we can see Elsie and Bessie for the position starts right here, but Moolinda starts right here. So what this is showing me is Bessie and Elsie, the position they're both starting is 0, but Moolinda is starting over here. So what we can imagine, what we can think about is, I don't know what this is. Let's just give it a random number, 20 meters. Moolinda has a bit of a head start. So if I were to draw this out, I'm gonna draw Bessie and Moolinda here. They're boxes, but Bessie and Elsie, Bess and L. But Moolinda is maybe starting over here, and maybe this is the finish line. Okay, so Moolinda, when the gun goes off, has a head start. That's what it looks like to me. Okay, let's look at Dolly. So Dolly is over here. And let's look again at the position and time. So we can see the position is the same. It starts at position 0, so starts at the same place as Bessie and Elsie. But it seems like Dolly is starting at a different time. Or there's a few things a Dolly can be doing. Maybe it's not allowed to move until 3 seconds. Or maybe Dolly, when the gun goes off, kind of doesn't move, forgets that it's in a race, and then starts to move a little bit later. So what would be happening is, let's draw it out. Let's have Elsie and Bessie here. They'd both go, and then Dolly would move 3 seconds after, or so forth. Okay. Okay, let's see what explanation I gave in the note. I'm going to clear all ink on the slide. Melinda seems to have gotten a head start. When the race started, she was already way ahead. When she did start moving, she was quite slow compared to other cows. Dolly, when the race started, she did not get going right, but took some time getting off the line. Okay? All right, let's continue. Okay, let's look at this example. The graph follows a path taken by a man. Match which story makes sense the most with the graph. Okay, so it seems like we have like 3 segments here. I'm going to call this 1, 2, and 3. Okay, so let's see what's going on. Let's look at A, I guess. A man is running and getting faster and faster over time. Okay, so that really shouldn't make sense. It seems like, okay, yeah, he could be running, but he's not getting faster and faster. At step 2, he's not really moving. So I'm not going to call that faster and faster. Let me also just change the color. Okay. Part B, let's look at part B now. A man is sprinting and getting slower and slower over time. I also wouldn't say that, because yeah, sure, he's running. He's not like, okay, kind of stops here, but then he goes again. So I'm not going to say he's going slower and slower. So let's look at something else. Part C. A man is running, takes a break, and starts running again in the same amount of time. And that looks kind of good. He's running, takes a break, doesn't move, stays at this position 20, and then runs again. But anyway, just to make sure, so I'm going to put a double asterisk here. But let's look at D. A man's running, okay, takes a break, okay, good, and starts running again in the opposite direction. Okay, that doesn't look good, because if it's the opposite direction, this should be going down now, and that's obviously not happening. He's not going down, he's going still straight. So I'm going to give C the answer here. Okay. Okay, let's look at this example. This next one, the graph follows the path taken by a mouse. Match which story makes sense the most with the graph. Okay, so part A here, a mouse sprints. Okay, kind of looks like that. We'll do different segments again. 1, 2, 3, 4. I'm gonna do a different color actually. We'll do this purple. A mouse sprints. Okay, looks like a very steep slope. So okay, takes a short break. Okay, yeah, takes a short break. Starts jogging back. Okay, very good. It's going from position 30 to position 20. So it's jogging back. Um, Takes another short break. Okay, that's good. Oh, this is 4, and this is 5. Takes another short break, then sprints back to where it started. Okay, that sounds very good. So that looks pretty promising. Let's read part B. A mouse is running. Okay, yeah, running. We could say that. Takes a short break. Good. Runs faster. Doesn't run faster. We can see that slope 3 is not as steep as slope 1. So can't be that. A mouse is running, gets faster. No, a mouse is running, then takes a break. So no, can't be that. None of the above. No, it looks like it's going to be A. Okay. All right. Another example here. Harry and Jim decide to go kayaking together during their Thanksgiving break. At what times are Harry and Jim in the same place? Okay, so when we're thinking about the same place, we're thinking about the position. We don't really care about the time in this scenario. So let's look at what point are they at the same position. And I'd say right around here at this 6 point, and this again is in kilometers, is when they're in the same place. Okay, so 1 hour, at what time, okay, are they in the same place? Okay, so at this 1 hour point, they're in the same place. How much time does Harry spend on the river before he passes Jim? Okay, so this is Harry in red here. I believe that's red. I am colorblind, so this is sometimes confusing for me. So this is Harry. And we can see that he's always kind of behind Jim at like time half an hour. Jim is all the way up here while Harry's over here, and always he's behind. However, at this 1 hour mark over here, it seems that they meet, and actually Harry gets in front of Jim. So how much time does Harry spend on the river before he passes Jim? There's a bit of a debate here we can say like that 1 hour mark, because if they both start at the same time at 0, then we can say 1 hour. Or let's say maybe Harry didn't get into the water until this point right here, then that would be a time from, I would say that's like 0.25 to 1. So that would be a time of 0.75 hours. So if you put 1 hour or 0.75 hours, I would have that acceptable. So where on the river does it appear that there might be a swift current? So when we're looking for a swift current or anything like that, what I would be looking for is in this graph, is there a point where they're both going faster? And how we can tell if they're both going faster at a certain point, that'd be when the slope is steeper. So I would say right around here, that's where there's probably a current. Where on the river does it appear that there might be a swift current? So I would say between position 6 and position 9. Again, I wouldn't be too crazy about exactly what you put, but yes, 6 kilometers to 9 kilometers where the slope suddenly increases. Okay, so personally, I wouldn't worry too much, but if you understand the concept of it, and especially put where the slope suddenly increases, that'd be correct. All right, guys, let's look at this next example. Jim is training for another race and decides to use an app to track his run. How fast did Jim run each interval? What was his average velocity? Okay, so I'm just gonna group these intervals 1, 2, 3, and let's get to it. I think you guys can do this by now. So please pause it to try to see if you got it right before I show the answers. But here we go. So part 1, I'm not going to go through all the steps anymore. I'm just going to kind of go through it a little bit more quickly. So number 1, we can see that the rise is going from 20. The rise is 20, going from 0 to 20 meters. And the run is going from 0 to 4 seconds. So this is just going to be equal to 5 meters per second. Okay. Number 2, velocity is, we can see the rise is actually not going anywhere. It starts at 20 and it ends at 20. So it's not, there's a run, it goes from 4 seconds to 10 seconds, or I should say 10 seconds from 4 seconds. However, there's no run, it's not moving in any direction, changing position, so this is just going to be 0. Number 3, we can see that the rise is going from 40, and it came from 20. So from 20, it went to 40, so we can see the rise is going to be equal to 20 meters. And then the run is going from this point right here, I'm going to say to half of this point right here. If you kind of felt tricked, like, or put 14, I'd say that's totally fine. It's not really drawn the absolute best, but I'm not going to say 13 seconds. Let me erase that. But what I'm going to say is the run is from 10 to 13. If you put 14, that's fine. It's not drawn the best. But the run I'm going to just put as 3 seconds. If you put a 4, again, that's fine. 20 divided by 3, 6.67 meters per second. Great. So what was his average velocity? So what we should know about average velocity is you're not just going to add all 3 of these numbers up and then you're going to divide by 3. That's what a lot of people do, and it's not correct. We want to find the total displacement and divide that by the total time. Okay, so total displacement, it goes from 0 all the way up to 40 meters. So I'm going to put 40 meters. And total time, it goes from 0 all the way to 13 seconds. Okay, if you put 14, again, I'm fine with that, but because the graph doesn't look the best. But for now, I'm going to just put 3.08 meters per second. All right, let's look at the next one. Okay, Jim continues his workout. Continue to find his average velocity for each segment. Okay, so we're doing 4, 5, 6, and 7. All right, so 4, we have velocity is the rise. So we're going from 0 to 5. So that's the rise. The run is going from 0 to 4. So it's going to be 4 seconds. So I'm going to do 5 divided by 4, and we get 1.25 meters per second. Number 5, again, there's no rise. It starts at position 5 and ends at position 5. There is a run. It goes from 4 to 8, but no rise. So this is just going to be 0. 6. Okay, 6 is a little bit tricky here. We see that it starts at 5 meters and ends at -30. So the rise, quote unquote rise, is going from here all the way to here. So the rise is, its change is, I'm going to say -35. Okay, so it's going down 35 from where it started. So I'm going to do -35 divided by the run, which is going from 8 to 12, which is 4 seconds. And maybe since this one's a little bit confusing, I'm going to write it all out. So again, velocity is equal to the final position minus the initial position, or the displacement divided by the final time minus the initial time. So final position is going to be this -30 here, minus this initial position, which is this 5 here, divided by the final time, which is this 12 seconds here, minus this initial time, which is this 8. So now I'm just going to do -35 divided by 4. This is kind of like how I had it originally, but anyway, I'm just showing more work right now. And we have -8.75 meters per second. I hope that didn't confuse people. Watch it again if it did confuse you. It should be fine. Okay. Oops, sorry. And the last one, part 7. Again, there is no rise. It's just staying at this -30 meters mark, and there is a run from 12 to 16, but no rise. So this is just 0. Okay. I found the average for some reason, -1.76, but it doesn't really ask for that. So, anyway, I'm just going to continue. All right, for the next 2 examples, Jim's mom will be reading Jim a bedtime story. Make a rough graph that shows the motion happening in each story. Okay, part 1. A man slowly walks. So we're kind of drawing a graph here. So try to draw this on your graph. I'm going to be explaining how it looks like step by step, but we're going to be drawing a graph here. And this is just like, a kind of a vague graph. So it doesn't have to be exact in any reason. It should just like look a certain way. A man slowly walks out of his house with his dog for 4 seconds. So in this graph, how I would personally be drawing this is a slope that's shallow like this. And since it says 4 seconds, this should be ending in the 4-second mark, okay, from the 0. Part 2. The dog stops to use the bathroom next to the fire hydrant and does his business for another 6 seconds. All right, this segment stops to use the bathroom. So I'd have it straight like this. And this should be going from that 4-second mark. So it does for 6 seconds. So that means it should go to the 10-second mark. Soon after, the dog sees a squirrel and sprints after it. The man sprints after the dog for the next 2 seconds. Okay, so it's a sprint for 2 seconds. So I'm going to do something very steep like this. And then this again starts at the 10-second mark and ends at the 12-second mark. The man stops the dog and scolds him for 2 seconds. Sorry, I didn't do this best, but yes, it should be a flat line from 12 seconds to 14 seconds. After getting strange looks from everyone, he realizes that he doesn't have a dog. So he starts to jog back home with his jump rope. This takes him 4 seconds. Okay, so he should be going back home. So going back to position 0. And this is from the 12-second mark to additional 4 seconds. So this should be 16 seconds. Okay, so that's what it should look like. It should end up looking something like this. It doesn't have to be exactly this. This is just a vague description of how it should look. The time should be correct. However, the position could be anywhere. It didn't give like the exact positions or anything like that. Okay, let's do this. A Bug's Life. An ant slowly sneaks into a grasshopper house and finds his way to the central office in 6 seconds. So again, we're doing a shallow slope here from 0 to 6 seconds. A giant grasshopper spots the ant and chases the ant out of the hut. The grasshopper continues to chase him out into the wilderness, which takes a total of 4 seconds. So this means he's going to be going backwards. So he's going to be going something like this. And he's going past the point in which he went. So giant grass spots the ant, chases the ant out of the hut. So that's where he started, the hut. The grasshopper continues to chase him out into the wilderness, which has a total of 4 seconds. So it should be out of the hut, so past the hut, past where he started. So this is going from 6 seconds to 10 seconds. The grasshopper catches the ant and leaves him buried in the ground forever. Okay, so the ant is just buried in the ground, so it's going to be in the same position forever. Okay, so it should look something like this. Again, don't have to be exactly, but it should look something like this. All right, guys, that's pretty much it for the graphs. I hope that you learned a lot. I hope you gained a lot of confidence from it. It can be confusing, but I hope you're doing a good job. Next time, we're actually going to be talking about acceleration. So I hope you guys are looking forward to that. Thanks for watching.